Let's talk about torque. This is a very important concept and one that you will be using a lot in the next unit, which is equilibrium. It's very important for equilibrium, but you're being introduced to it now in this unit, the rotational unit here. Strictly speaking, torque is the rate of change of angular momentum. But in layman terms, what we're really talking about is if you have an object, say, that is not rotating, and you want it to rotate, then you must create a torque. And you create torques by exerting forces. For example, if I exert a force on the propeller, then it starts rotating, because the force I applied created a torque which made it start rotating. The formula for torque is the force times the lever, we use R for the lever here, times the sine of the angle between the force and the lever. So what is the lever? The lever is the distance between the rotational axis and where the force is applied. Let me do an example. Let's look at a simple situation. Let's just say we've got a board like so. This will be right here, this will be the hinge, which is going to be our rotational axis. And let's say that I apply a force upwards on this board. So this force is being applied some distance from the rotational axis. So from here to here, that distance is the lever. And you can see that this lever is going to be horizontal. So this angle here is the angle between the lever and the force. So I've got a horizontal and a vertical. The angle between them is 90. That would be the angle I'd put in there. And of course the sine of 90 is 1. Now let's think about our goals with torque. Typically you're going to want to do, in practical situations, you're going to want to do one of two things. You're going to want to maximize the torque, or you're going to want the torque to be 0. If you want to maximize the torque, obviously more force means more torque. That's pretty straightforward. But also, you want a big lever. The bigger the lever, the bigger the torque. This is why on doors, where do we put the handle? We put it here on the side of the door that is furthest from the hinges. That maximizes the lever. If you go over to England, for some reason, sometimes they put the doorknob right in the middle of the door. I have no idea why. This makes it more difficult to open the door. It's better to have it here because you're maximizing the lever, and thus you're maximizing the torque that can be created. The other thing you want to do is you want your sine function maximized. The maximum value for sine is 1, and that happens when theta is 90, which means you want your force to be applied perpendicular to the lever. Now, if you don't want to create a torque, which there are situations where you don't want a torque to be created, okay, well, obviously you could just not exert a force. That's the trivial case. No force, no torque. Pretty straightforward. You could also make R 0. What does that mean? Well, if the lever is 0, that means you're applying the force right at the rotational axis. If you apply the force right at the rotational axis, your lever will be 0 and your torque will be 0. The other thing you could do is you could apply the force parallel or anti-parallel to the lever. So if I'd applied a force that went this way, or if I applied one that went this way, either case, both of these would create 0 torque, because one has an angle of 0 with the lever, the sine of 0 is 0. The other one has an angle of 180 with the lever, the sine of 180 is 0. So if you're applying your force parallel or anti-parallel to the lever, then no torque will be created. If you apply the force at the rotational axis, R will be 0. No torque will be created. This, is, by the way, is akin to trying to open a door by pushing on the hinge. It's just not going to work. You're not going to open the door. You're not going to have any luck. Now, a couple other things about torque I need to mention. The units. Torque is measured in Newton meters. Also, torque is a vector. This formula that I've put here, I didn't talk about the vector nature. It's not a vector formula, so there was no reason to bring up the vector nature of it, but torque essentially can be clockwise or counterclockwise. In this case, this force wants this beam to rotate counterclockwise. So this is a counterclockwise torque that is created. And of course, you decide which direction is positive. If you want to call counterclockwise positive, that's fine, but that means clockwise is negative. We have another formula, though, that does account for the vector nature of torque. That formula is the net torque, and it's written this way. Torque equals I alpha. Once again, we have the moment of inertia, which I talked about in the rotational kinetic energy video and also the angular momentum video. And alpha, this is angular acceleration. Notice this looks a lot like Newton's second law, only Newton's second law says the net force equals ma. Okay. This is essentially Newton's second law for rotation. This is Newton's second law, this is Newton's second law for rotation. And so the net torque, we would combine together all the torques, taking into account, whether they're clockwise or counterclockwise. The last thing I need to mention, which is very important, vitally important for torque, and that has to do with gravity. Sometimes you're going to be dealing with gravity acting on something and it's going to create a torque. For example, just on this pen here, if I hold the pen at the end, gravity is creating a torque on it, it's going to cause it to rotate down. Okay. So the thing I need to mention is that for gravity, we always treat it as pulling from the center of the object. So here, the center of the object is right there. So that would be where F sub g is acting. And so the lever is from the rotational axis to here, or in other words, halfway. Now, to be precise, gravity pulls from the center of mass. Unless you are told otherwise, the center of mass will always be the geometric center of the object. You do have some problems in the equilibrium homework where it's not the geometric center. At the geometric center, the center of mass is somewhere else, but it's clearly indicated in those problems. So unless you're told otherwise, you always treat gravity as pulling from the center, and so the rotational axis is always going to be, in this case, it would only be half of the overall length of the board.